Welcome to Saitechinfo channel, my dear students. In this tutorial, I'll be discussing about Carnot engine, Carnot cycle and its efficiency. Let me consider this heat engine. The heat engine is a device that converts the heat energy into a mechanical energy. Carnot, he devised an ideal engine, that is an engine with the ideal cycle of operation. So he designed a heat engine in such a way the efficiency of that engine is 100%. Here, look at this diagram. This is the flow chart of Carnot engine. T1 is the source. This is the source. This source is duly insulated, but it is at the top. It allows the temperature, the heat to transfer. It means conductive material. The side portions are totally insulated. Source, it is a hot body that is kept at T2, T1 temperature. So let us call the temperature of the source is T1. And sink, this is the sink. This sink is also insulated, but it has the conductive material at the top. So that when you keep the piston and barrel assembly, that is piston and cylinder, either on the source or on the sink, it can transfer the heat energy. If it is kept, this piston and the cylinder is kept on the source, it can transfer the energy, heat energy from the source to the cylinder. And when we want to deliver or transfer the heat energy from the cylinder to the sink, we can compress it and thereby we can transfer the heat energy. Do you understand? Now, the source, it is said to be a hot body which is kept at a constant temperature T1, as I already mentioned. And what about sink, where it receives the heat energy? So it should be a cold body which is kept at lower temperature. So it should be comparatively at lower temperature. So T2. So this is T1 and T2. So it means T1 is greater than T2. So T1, the temperature of the source. T2 is the temperature of the sink. In between that, we have got the totally isolated, that is totally insulated stand. Okay, right. Now let us move. The cylinder is made up of non-conducting material, non-conducting walls. So this is the cylinder. The side walls are totally insulated, non-conductive. But at the bottom, it is conductive, so that it can transfer the heat energy. And you have got the frictionless, weightless piston. Okay. Now, when you press it, that is compress it, there is an increase of pressure. When you expand, there is a decrease, there is a drop in pressure. So you have got the working substance inside the cylinder. So this is the setup. And as I already mentioned, we have got the insulated stand. And it is totally adiabatic, in order to perform the adiabatic operations. Adiabatic operations. Now let us explain about the working of Carnot engine. The Carnot engine has 4 important operations, or we can say stages. The first one is isothermal expansion. Now what we do is, we take this piston and barrel assembly and keep it on the source of heat energy. Then at constant temperature, we slightly, that is, expand isothermally. At constant temperature, we expand it. And then we keep on the stand and further expand it, but there will be a change in heat, is it not? And not only that, this is an expansion taking place at adiabatic system, because you have got the adiabatic stand where you can further expand it. The third one is isothermal compression. So what I do is I keep this cylinder on the sink and compress it. Are you able to follow? So when I compress, what happens? Pressure increases. Is it not? Right. And the energy is transferred to the sink. Is it not? So it is carried out at the same temperature. That is isothermal compression. Once again, I take this and keep it in the stand, on the stand, and further compress it. So it means I am doing this compression at adiabatic system, on an adiabatic system, in an adiabatic way. It means there will be a drastic change in the temperature, is it not? It is not taking place at constant temperature. So here isothermal, whereas on the stand, since it is totally insulated and the side walls are also insulated, so we can expect adiabatic compression and expansion only. Now let us look at the graph. See, that is when I keep the piston and barrel assembly on the source. So I did the expansion, that is isothermal expansion. Is it not? So A to B. So when I do this, what happens? Pressure comes down. Is it not? And there is so pressure comes down, volume increases. Are you able to follow? So this is the direction. Okay, this is the direction. And then let us consider the next one, that is adiabatic expansion. So what about this one? This is isothermal expansion, and A to B. Okay, so you can find there is a change in the pressure from P1 to P2. So this in the A and B அப்படிங்கிறது isothermal expansion. So isothermal expansion we have volume 1, volume 2. There is a change in volume. There is a change in pressure P1 to P2. Okay, and that can be represented as, and during this there will be a heat transfer from where? That is from the source to, I am keeping the stand here. That is, the piston and barrel assembly is kept over the first one, the source. So there is a transfer of heat to the system, working gas, is it not? So that is represented as A to B. Are you able to follow? Now volume is increasing from V1 to V2. Pressure is decreasing from P1 to P2, is it not? So you can mention the pressure here. See this? This is the pressure, P1 stage. From P1 to, now it has come down to P2, is it not? So P1 to P2, there is a drop. And what about volume? It has increased from E to G, is it not? So there is an increase in volume, E to G, because x-axis is volume and we have mentioned y-axis as P. Okay, right. Now the quantity of heat transferred, and that is the work done. So the work done is given in an isothermal expansion as PdV, integral between the limits of V1 and V2 of PdV. Is it not? and we already know that is PV is equal to nRT, is it not? Where N is equal to number of moles. So PV is equal to nRT. When N is equal to 1, you can put RT. So instead of P, you can put that is RT by V. Is it not? RT by V. So that is P. So this P is replaced by RT by V and is further integrated here. Okay. So 1 by V. This is 1 by V. On integration, it becomes logarithm to the base E. That is natural log. That is V between the limits. So here got limits V1, V2. So that these things we already explained. So we have once again V1, V2. Now substitute the value. So log V2 by log V2 minus log V1, and you can adopt the quotient rule in logarithm. So according to the quotient rule, the subtraction can be converted into a quotient, is it not? So log V2 minus log V1 is converted as log of V2 by V1. Do you understand this? So which is nothing but the area under the curve A, B, and then you have G, E, A. That is this curve. Do you understand? So this is the work done during what? Adiabatic expansion. Is it clear? Sai.
Yes, sir.
Right.
Sir, only A, B, G, E, and A. is that-
ஆமாம் அந்த ஆமாம் சாரி இது வராது இந்த கர்வ் கடையில்
ஆமாம் சார். sir, இந்த curve வரைக்கும்.
அங்கே வராது, நீ அது மாதிரி ஷேட் பண்ணிக்கோ, இதோட நிறுத்திக்கணும். அதான் ஏரியா அண்டர் த கர்வ் ஏ பி ஜி இ ஏ, தட்ஸ் ஆல். Okay, so that represents the work done in isothermal expansion. Are you able to follow? Now let us go to adiabatic expansion. That is, we keep that what do you call that piston and barrel assembly on the stand. So when you keep it on the stand and further expand it, okay, so when you expand it, moving up the piston, what will happen? There is no, the heat transfer is affected here, is it not? And not only that, the temperature, there is a change in temperature also. Okay, so what happens here? There is a change of temperature from T1 to T2, is it not? So from here to here, so when it is in T1 stage, now it becomes T2 stage, right? Okay, so now we have to consider the curve B to C, because this is further expansion. You can find in this expansion there is a drastic decrease in the pressure. Are you able to follow this? Here there is a slow decrease. Here you can find the drastic decrease but steady increase in the volume from G to H, that is from V to V3. Are you able to follow? So this stage is, so this is P3. So from P2 to P3 it has come down drastically in adiabatic expansion. And not only that, in this case, that is, the volume has increased from V1 to V3, is it not? V1 to V3. Got it? Right. And now let us apply the equation. Work done is equal to W2 is equal to, let me call W1 as work done in isothermal expansion, W2 work done in adiabatic expansion. That is when I keep the cylinder on the insulated stand and further expand it. So that is the work done, W2. So this is integral between V2 and V3, PdV. And this P is already, that is, we have discussed under adiabatic expansion, work done in adiabatic expansion. So that is equated to R divided by gamma minus 1 into T1 minus T2, where the gamma is nothing but, that is, Cp by Cv. What is Cp? Cp is the molar specific heat capacity at constant pressure. Cv, the molar heat capacity at constant volume. So the ratio between these two is gamma. Do you understand? So gamma minus 1, and we have got the complete derivation for this, and you can refer to that particular video. Then T1 minus T2. So this is the area under what? BCHB. So B, C, H and then G, B. So we can mark like this. Okay. So only this area. So area under this curve, you can observe the work done is less in adiabatic process. Do you understand? Just by looking at the curve, the area under the curve of isothermal expansion curve, and compare with the adiabatic curve, the area under the adiabatic curve, you can find the vast difference between what you call this isothermal and adiabatic. Do you understand this? Right. And then now let us move to the third one, that is isothermal compression. Okay. So are you able to understand so far? If there is any doubt, you can ask me.
Yes, sir.
Okay. So let us move to the next one, that is the third stage. What is the third stage? Isothermal compression. What am I going to do? That is, we are going to place, let me go back here. So I am going to place this cylinder here. Okay. So place this cylinder, and I am going to compress it now. So this is called, and I am doing this compression isothermally at constant temperature. Do you understand? So at constant temperature, when I do this compression, so Q2, that is work done, that is W3. So this is W1, this is W2. Now I am talking about compression W3. Are you able to follow? So probably that is, you should notice this. A to B is what? Expansion. What type of expansion? Isothermal expansion. And what about this? This is adiabatic expansion. This is also expansion, but this is adiabatic expansion. What about this? This one is isothermal what? Isothermal compression. What about this one? This is adiabatic compression. Are you able to follow? Now we are talking about C to D. That is the third stage. So I am keeping this piston and barrel assembly on the sink and compressing. So when I do the compression, what happens? There is an increase in the pressure from P3 to P2. Is it not? So P3 to P2, it has P4. P3 to P4, it has increased because of compression. And the volume has come down to V3 to V4. Are you able to follow? V3 to V4. Right? Okay. So upward there is an increase in pressure, and here towards right there is an increase in volume. Now the volume has come down. Are you able to follow? So this is the fourth stage. So third stage V4. So V3 to V4. So that's why we have put that is isothermal expansion. Is it not? V3 to V4. So where minus PdV because compression. So that is equal to minus RT2 log of, we know all these equations. So V4 divided by V3. That is minus area of what? CDHC. So what is the, can you identify the area under the curve of CD? That is this one. Let me take in a different color. Okay. Do you understand this? So this area. So this area indicates what? Isothermal compression work. Is it not? So that is C and then D, C, D, then F, H, again C. Do you understand? So that is this one. And the negative sign indicates that is the work is done on the working substance. The work is done on the working substance. Okay, right. Next, now let us see Q2 is equal to RT2 log of V3 by V4. So this is the Next equation. Then adiabatic compression. So adiabatic compression means D to A, right? So D to A I can indicate like this. And what is the curve here? DA is the curve. So area under the curve, this is the area under the curve. Are you able to follow? So you can find these two types of compression. And what about the work done? Work done in adiabatic compression is represented here as a blue line. And red lines indicates area under the curve. That is work done in isothermal compression process. Are you able to follow? Now when you compare these two, probably you will understand that isothermal compression work is more than that of adiabatic work. Do you understand? Right. Now adiabatic compression, where W4 is treated. So here V4 to V3 minus PdV, that is equal to minus or gamma divided by gamma minus 1, and there is a drop in temperature T2 to T1. So T2 minus T1. So again negative sign indicates the work is done on the working substance. Okay, right. Now W4 is equal to R divided by gamma minus 1 into T1 minus T2, and this area, that is this one, A, D, A, E, F, D, that indicates the adiabatic compression. Okay, now we have explained about the 4 stages of operations in Carnot cycle. Is it not? What is the first stage? Isothermal expansion. Next stage, so we can call it, this is stage number 1. What is this stage number 1? Isothermal expansion. Stage 2, adiabatic expansion. Stage 3, isothermal compression. Stage 4, adiabatic compression. Do you understand this? Are you able to follow? Right. Now let us move further. See, we need to talk about we discuss about the work. Now we need to compare, that is what is the quantity of heat transferred and what is the quantity of work done. So whatever the amount of heat transferred should be completely transferred into converted into the work. So that means it has got the 100% efficiency. So efficiency of Carnot cycle, that is, it is given by eta. So eta is equal to heat converted into work, which is nothing but Q1 minus Q2. It can be represented in terms of Q. So Q1 minus Q2 divided by what is the heat drawn from the source originally, that is Q1. Therefore eta is equal to Q1 minus Q2 divided by Q1. Okay. Now we can split this fraction so that Q1 by Q1 minus Q2 by Q1. Q1 by Q1 cancel, that is 1. So 1 minus Q2 by Q1. So that's what given here. So eta is equal to 1 minus Q2 by Q1. Okay. We know already Q1 by Q2 is equal to W1 by W2, that is nothing but RT log of V2 by V1, and this is RT2 log of V3 by V4. So we can suitably substitute also, and R can be cancelled here. Therefore T1 by T2 into log of V2 by V1, then T2 by T2 log of V3 by V4. Okay, right. And next, here in case of adiabatic expansion, so we already discussed regarding adiabatic processes, where TV power gamma minus 1 is equal to, that is T1 V2 power gamma minus 1 is equal to T2 V3 power gamma minus 1. So because TV power gamma minus 1 is constant according to adiabatic process, and this gamma is nothing but Cp by Cv. So now we have this equation. So T1 by T2 is nothing but V3 by V3 power gamma minus 1, V2 power gamma minus 1. Okay. So similarly for dA, now that lies under the adiabatic curve dA. So T1 V1 gamma power minus 1, V1 power gamma minus 1, that is equal to T2 V4 power gamma minus 1. Therefore you can bring this T to this side. So T1 by D2 is equal to V4 power gamma minus 1, V1 power gamma minus 1. Okay, so we are completely relating with the adiabatic. Therefore, by comparing these equations 6 and 7, we are able to get V3 power gamma minus 1 V divided by V2 power gamma minus 1 is equal to V4 power gamma minus 1 V1 power gamma minus 1. So you can completely eliminate this gamma minus 1, power gamma minus 1, so that we have V3 by V2 is equal to V4 by V1. And we can reciprocate also. So V2 by V3 is equal to, that is V3 by V4. V2 by V1 is equal to V3 by V4. Now we can substitute in the original equation where we discuss about the ratio of, that is V2 and V3. So that can be eliminated by introducing this V3 by V4, and you have got already V3 by V4, is it not? Now Q2 by Q1 is equal to T1 by T2 by T1. So you can further reciprocate it. Q1 by Q2 is also equal to T1 by T2. So likewise, now what you can do is you have Q2 by Q1, add 1 on both sides. Similarly, T2 by T1, add 1 on both sides. Is it not? So that you can get Q1, Q2. So instead of adding 1, you can subtract also, so that we can get the efficiency, right? So subtracting 1 on both sides, okay, and you can interchange also. So introduce minus on both sides and add 1 on both sides. Are you able to understand this? Sai, do you understand, or shall I explain once again? That is, you have Q1 by Q2, here T1 by T2. What I am doing is just I am converting this into, now introduce minus on both sides and add 1. Okay, now we can take LCM. So Q2 is the LCM, therefore Q2 minus Q1 is equal to, here T2 minus T1 divided by T2. Okay, so this can be represented in this way also. Are you able to follow? Now we already know that is eta is equal to 1 minus Q1 by Q2. So that eta can also be represented as 1 minus T2 minus T1 according to this equation. And once again you can take LCM and convert this into a temperature term. So efficiency can be represented in two ways. One is in terms of temperature T1, T2, otherwise quantity of heat transferred. So from Carnot cycle, we have some inferences. Let me explain one by one. Efficiency of Carnot cycle is independent of the working substance. That is point number 1. But it depends on the temperatures of the heat source. Is it not? So it depends on T1 and T2. Second point, efficiency of Carnot cycle will be 100% when T1 is infinity or T2 is 0 Kelvin. How is it possible? Let me take this efficiency. So efficiency is equal to, we have got efficiency is equal to T2 minus T1 divided by T2. Is it not? So when T2 is equal to 0 Kelvin, what happened? Anything divided by 0 is infinity, is it not? Okay. So, and when T1, and here you have, that is a T, it should be T1 here, T2 by T1. Okay. So I must explain as a T2 by T1. You can change it. So here this should be T2 by, because that is the original temperature, is it not? So efficiency is equal to T1 minus T2 divided by T1 here. So when T1 is equal to I mean, that is infinity. So T1 is equal to infinity means what? Anything divided by infinity becomes a 0. Is it not? So in that case, efficiency will be 100% here. Okay. Or when T2 is equal to 0 means that is once again it becomes 100%. T1 by T1 is equal to 1. Means eta is equal to 1. And similarly, third point, neither temperature of heat resource can be infinity. It is very, very difficult to get the infinite amount of heat. Is it not? So T1, that is the source temperature. Is it not? So can you make it infinity? It is very difficult. So as neither of the temperature of heat source can be infinite, nor the temperature can be made 0. So T2, so we have got two positions, this is the source, this is the sink. Can you make a infinite temperature? No. Can you make absolute 0 Kelvin temperature of sink? That is also ruled out, is it not? So that is why, as neither of the temperature of the heat source can be made infinity, and nor the temperature of the sink can be made 0 Kelvin, the inference is that Carnot engine working on reversible gas cannot have 100% efficiency. This is hypothetical, highly imaginary. And that's why it's an hypothetical engine, that is imaginary engine. It means that it is impossible to construct a mission to achieve this 100% efficiency unless otherwise it is supposed to be a perfect Carnot engine. That is ruled out. So do you understand this? Okay.
Yeah.
Okay, so let me ask you some questions based on this. What are the 4 stages of operations in Carnot cycle?
Isothermal expansion, adiabatic expansion, thermal compression, and adiabatic compression.
Okay, so there are 2 types of expansion and 2 types of compression. Okay, right. And in isothermal, compare the work done by isothermal expansion and adiabatic expansion. Which is greater?
Isothermal expansion.
Isothermal expansion is greater. Work done in isothermal process is greater. Okay, so thank you.
Thank you, sir.